question. Right? So, if at some point you don't understand, I know what I'm doing. He knows what he's doing. If y'all don't know what you're doing, you got to raise your hand or something saying, hey, wait, stop, can you do this one more time? Okay? Has everybody got a calculator or cell phone that'll do calculators or something like that? I'd prefer the one that you would use on a test, right? So, probably not your cell phone, but so something you can calculate with. All right, and then I just want to know what comes to mind when y'all hear acid. Hydrogen ions? Well, you know something about acid. That's not what comes to mind when I hear acid. I think like lemon juice and that kind of thing. So anything else come to mind when you hear acids? What do you think of like flavor of acids? Sour, right? Like citric acid, okay? What are some acids you enjoy eating? Like hydrochloric acid, stomach acid is not one of those things you enjoy eating. If you've ever thrown up hard enough for it to go through your nose, that's not an enjoyable thing by anybody. So hydrochloric acid that you probably did in lab, we're not going to worry about. So what's an acid you might enjoy eating? You brought up citrusy things. Pineapples. So you got citric acid and ascorbic acid, that's vitamin C. Any other acids you enjoy eating?
Vinegar.
Vinegar's delicious. We would call that acetic acid to be chemistry fancy kind of thing, like vinegar chips. Anything else you just really love? Yogurt. Okay. Yogurt is lactic acid. It's got the acid that we take milk sugar from and turn it into an acid. So lots of things out there that we enjoy eating. Can y'all name a couple bases you may or may not know?
Like baking soda?
Baking soda is kind of basic, right?
Like detergents.
Detergents, some of them have basic qualities to them. Some of them have acidic qualities, actually, based on what you're trying to do, but a lot of them have a basic. Anything else? Y'all heard of lye before? Right? Lye is a very good base. Drain cleaner as well, right? So, all right. So, we've got this concept of what is an acid and what's a base. So what's an acid? Exactly what you said. An acid is something that gives away hydrogen ions. So far so good. A base is therefore the opposite. A base is something that accepts hydrogen ions. So if you're capable of accepting a hydrogen ion, that makes you a base. If you're capable of giving a hydrogen ion away, that makes you an acid. Right? So, okay. Let's see if we can do a conjugate acid-base pair. And you mentioned that they had done that in Unit 4. So let's do, this is acetic acid, by the way, because I'm really lazy. Right? So, and if I mix it with H2O, who do you think is going to lose the hydrogen? The acetic acid or the water? Acetic acid. So it's going to turn into the acetate ion, and this becomes this funky thing that we call the hydronium ion. So it's important that you know the name hydronium. It's not important. But this is the same thing as a hydrogen ion. So if you see this, same thing as a hydrogen ion. Okay? Hydrogen ion is a naked proton. So technically you don't actually see those in solutions. Like you don't just see a proton running around. It usually grabs onto water. So technically this is the most correct version, but nobody's got time for that. So can anybody find me a conjugate acid-base pair?
That would be acetic acid and the acetic ion.
Okay? Right? So that would be the conjugate acid-base pair. Easy enough? The thing that gave away the H is the acid. The thing that it becomes is the conjugate base. Okay? Can anybody name me another one?
H3O plus and H2O.
Right. This is the base. Water is the base in that case. Because it accepted the H and it becomes the conjugate acid H3O. Easy enough? You now get 1 point on the AP exam in 2019 because you can do it. So far so good. All you need is 99 more points to make a perfect score. Okay? Okay. All right, now, what do y'all remember about equilibrium? I know it's been a while. I know it was a while, but I heard that y'all had a really good grounding in it. So what does big K mean to y'all in terms of equilibrium?
Constant.
Yes, it's a constant, but like if the number is big or small, what does it mean to you?
Which way it favors?
Which way it favors, okay?
Instead of the word way, use a different word. What do you mean by which way? Like
Which
up,
is
down?
reactants.
Product versus
Okay,
reactant.
products versus reactants. So let's just make up a number. Let's call it 3.5 times 10 to the negative fifth. Let's just make up a number. Okay. So the Ka for this reaction is 3.5 times 10 to the negative fifth. What does it mean to y'all that that is the number? What does that tell you about that reaction?
It's a fraction, isn't it? So
It's a smaller than 1, right? It's less than 1.
So it means that whatever is in the denominator is very large.
Okay, that's good
Reactant
thinking.
favor.
I can't remember if it's reactants or
I think
products.
it's a
Oh,
reactant.
well,
favor.
let's do that real quick. Let's write the K expression for this sucker. We're going to use Ka. It's the acid K. Do they have the reference sheets in front of them?
They do.
Okay. So y'all find that there's should be a K expression. And since you couldn't reference products over reactants or reactants over products, it's good news. So what's going to be the expression for this sucker?
H plus, or concentration of H plus
Okay.
times concentration of A minus over concentration of HA.
Okay. And HA in this case is acetic acid, right? And why didn't we put water in there?
Because it's just acid.
Nope.
Oh, this is equilibrium stuff.
Mm-hmm. I'm just tying it back. If y'all remember, when we write equilibrium expressions, it could even be like KSP, that kind of thing. We never include pure solids or pure liquids. So we don't include water because what's water? It's a pure liquid, right? You can't have a concentration of something when that's all there is, right? Water dissolved in water is not a solution, it's just water, right? So that's the K expression. So now going back, what does it tell you that this number is so small? 3.5 times 10 to the negative fifth, pretty tiny number.
There's a lot of acetic acid in the equilibrium because it's in the denominator.
Okay, so does it favor reactants or products?
Reactants.
Okay, so if we drew the arrows, it would look something like that. Most of it is going to stay reactants. In other words, not very many of these H's will come off. Very few of those hydrogens will come off. Most of them will stay bound to the acetate ion. So y'all remember that from equilibrium, it favors one side or the other, that kind of thing? Okay, so acetic acid is one of those things that we call a weak acid. Why are they weak? Well, it's weak because not very many of the molecules give off the hydrogen ion. Most of them stay attached. So what do you think would happen for a strong acid? A strong acid, would it have a big Ka value or would it have a small Ka value?
Larger than 1.
Right? We'd expect it to be pretty big. So let's just look at a list of all the acids we've got out there. So, did y'all ever get to play with hydrochloric acid?
Yes.
Right? So that's 1,000,000, 1.3 times 10 to the 6th. Do you think that's a pretty big number? Greater than 1? So that's a pretty big number. All right. Hydrobromic acid, HBr, is 1,000,000,000.
What does large mean?
Hydroiodic is 3 billion. And then perchloric is large. If you ever get on a bathroom scale and it goes large, then what that means is you've exceeded that scale's ability to measure you, right? So my daughter's a type 1 diabetic, and when she was 10, she went something called DKA, diabetic ketoacidosis. We didn't know she's diabetic at this point. We take her to the doctor. They use one of those prick your finger, stick some blood in it, tells you your blood sugar. It just said high. She had so much blood sugar that it was outside the range of what they could measure, right? So large That's a pretty strong acid. So y'all need to know your strong acids. So let's make a list. Strong acids. Hickel, Hibber, high. Hickel, HCl. Hibber, HBr. High, HI. If you're thinking about the periodic table, Hickel, Hibber, high, right? 3 of the halogens, Cl, Br, and I. Those are all strong acids, meaning they give away the hydrogen ion like more than 95% of the time. If you stick 1 mole of HCl in water, you're going to get 1 mole of hydrogen ion. You're going to get a butt ton of hydrogen ion.
So 100% dissociation.
Right. Yeah.
Is there a reason worth mentioning why hydrofluoric acid isn't in this group?
Yes. We'll get there in a minute. So Hickel, Hibber, high, y'all know that. The other 2 y'all need to know are nitric, HNO3, and sulfuric, H2SO4. And obviously perchloric is HClO4. You can know that's a strong acid as well. But the reason why we want y'all to know the strongs is because anything that's not strong is by definition weak. Right? So if I said acetic acid, you're going to go, well, it's not one of the strong ones, then by definition it's weak. Right? So Hickel, Hibber, high, sulfuric, nitric, and then perchloric.
So you could also probably add that the Ka is going to be larger than 1 for all of these.
Well, and on the AP exam, they largely don't give you a K value for an acid like that. They just expect you to know the strong ones. Okay? Reasonable so far? Yeah? Okay. Now, let's talk about if this is the acid, perchloric acid, then the ClO4 would naturally be the conjugate base. Everybody agree with that? Okay. Now, some books will tell you that strong acids give off weak conjugate bases. That's not true at all. Strong acids give off bases that are worthless. Okay? Strong bases give off acids that are worthless. Sorry, my bad. Wait, slow. Strong acids give off conjugate bases that are worthless. They don't do anything. They don't do anything at all. They don't have any effect at all on pH. So if you add a bunch of chloride ion to a solution, doesn't affect pH at all. It's such a worthless base, no one cares. Right? Can I prove that to you mathematically real quick?
Yes.
Okay. There's a mathematical formula that says that Kw is equal to Ka times Kb. Okay, it's on your sheet. And Kw at 25 degrees is 1 times 10 to the negative 14. So y'all are going to pick an acid for me. Pick one of the strong acids.
Hydrochloric.
Hydrochloric. So hydrochloric, I'll even make the math easier for you. Hydrochloric, its Ka is 1,000,000. 1 times 10 to the 6th. Can y'all please calculate the Kb for hydrochloric acid? Go ahead and calculate the Kb for hydrochloric acid if the Ka is 1.3 times 10 to the 6th. And if you want to be lazy and just make it 1 times 10 to the negative, or 1 times 10 to the 6th, no one cares.
1 times 10 to the negative 8th.
I got 8 or 7.7 times 10 to the negative 21, but that could be totally wrong. Okay,
If you just
7.7.
no, if you just use 1, you should get the answer 1 times 10 to the negative 20th. So your 7.7 times 10 to the negative 22nd is right on. Now, would you call that a big number or a small number?
Small.
Small or incredibly small?
Incredibly small.
Incredibly small. In fact, so small that it would make whatever base there is there almost worthless. Because that Kb value describes how apt is that thing to reach out and grab a hydrogen ion and do something with it. So strong acids give off bases that are worthless. They don't do squat. As we say in my classroom, diddly squat. Okay? Now, What about your weak acids? Well, here's a weak acid, ethanoic acid, 1.8 times 10 to the negative 50. Y'all go ahead and calculate the Kb for acetic acid, ethanoic acid. If the Ka is 1.8 times 10 to the negative 5th, I couldn't remember the number, but I knew it was times 10 to the negative 5th. Go ahead and calculate the Kb for acetate ion. What'd you get?
I'm getting 5.6 times 10 to the negative
5.6 times 10 to the negative 10. Fail. All right. Y'all need to sing out if you're having calculator problems, because if you're not getting about that answer, because we need to fix that before May the 2nd. May the 2nd, right? So usually it's just finding that button that means I can do exponents kind of thing, right?
Wait, when you put the 1 times 10 to the negative 14 up there for KW, it sounded like you had some context behind that number, but I think I missed it.
Oh, it was at 25 degrees, and we're going to get into that in just a second.
And then so that's just a constant?
It's a constant at 25 degrees. Because if y'all remember from equilibrium, K is the equilibrium constant. And what's the only thing that can change the K value of K? Temperature. So if we change the temperature, KW changes. But if you look on your reference sheet, it probably says something like KW is 1 times 10 to the negative 14 at 25 degrees Celsius. And that we just call that standard temperature, right? So. Now, this is 5.6 times 10 to the negative 10th. That means this base does something. I'm not saying it's a strong base. I'm not saying it's going to clean out clogs in your drains. It's not a strong base. Weak acids give off bases that do something. So strong acids give off conjugates that are worthless. Weak acids give off conjugates that do something. That seem reasonable so far? Okay. All right. So phosphoric acid. Y'all ever drank that before?
Yeah.
Phosphoric acid. You ever had phosphoric acid before? Mountain Dew Mellow Yellow? Yeah. You know why they can put it in there? Because it tastes zingy on your tongue and it doesn't kill you. If they put this in there, that would not feel good, right? Methanoic acid is very weak. Benzoic acid is very weak. Okay, so carbonic acid is the one your blood makes when it mixes carbon dioxide and water. And it's pretty weak because it doesn't eat your flesh apart when you make it in your body, which is a great thing, right? Also, carbonic acid is what you find in soda when they put the carbon dioxide in the water. So you are a soda, but without the Mentos, right? Although that would be cool, right? If you could swallow Mentos and it comes spewing out of orifices. I mean, not for you personally, but for the other people around you, that would be like, oh, that's cool. All right, so let's look at some of the math that we need to be able to do. So KW is, and this is on your sheet, right? So you're going to have this on the exam. We're going to write KW is multiplying these two things together. So y'all have already shown me that y'all can do this math. I'm okay with that. Your pH scale. What do you know about pH scale? Go 0 to 14. Very close. 0 to 14.
7 is neutral.
7 is neutral. So 0 to 7 is acidic, right? The lower the number, the more acidic it is. And since it's a log-based system, that means it's powers of 10. So if you have a pH of 6 and she has a pH of 3, it's not like, that's pretty close, 6 and 3. It's 10 to the third different from each other, right? So if she's 6 and she's 3, then that means that she is 10 to the third or 1,000 times more hydrogen ions than she is. So a little change in pH is a big thing. So far, so good? All right, good. So let's see if we can do one of those. Find a pH. So I'll put up a couple numbers. Let's go. Find the pH of 1 times 10 to the negative fourth, 1 times 10 to the negative third, and then 5 times 10 to the negative third. Go ahead and find those. Those are all hydronium ion or hydrogen ion concentrations. So go ahead on your calculator, try to take the negative log of those values. And is it safe to say that all of y'all have had Algebra 2? So would you say you kind of know what logs are, or would you say I just know where the log button on my calculator is?
No longer.
Okay, all right, good. Because it could go either way. Both will get you to an answer on the test, right? So what y'all get for 1 times 10 to the negative fourth?
4.
Nope. 4 point something. 0. So let me tell you something about logs, and this is why I was asking the question. This 4 talks about that exponent. The number just 4 has no significant digits at all. That 4 just talks about that exponent. So what is the log of 1? Well, a log is saying 10 to the what power is 1. So 10 to the 0th power is 1. So really, everything to the right of the decimal describes this number. Everything to the left of the decimal describes the exponent. Okay? What y'all get for this one down here, 1 times 10 to the negative third?
3.0.
3.0. How many of y'all tried to do that in your head because you were feeling confident? I need y'all to be more confident. 10 to the what power is 10 to the negative third? Negative 3, right? And so it's the negative of that value. So on the multiple choice, you don't get a calculator, and I'm not going to ask you to take the log of 17.3 times 10 to the negative 16. Nothing like that. But you ought to be able to take the log of that in your head, because you understand what a log is. What'd you get for this one?
2.3.
This one? Okay. Is 5 times 10 to the negative third in between these two numbers? One times 10 to the negative third is small, and then 5, and then 1 times 10 to the negative fourth is bigger. Is that right? Okay, y'all are nodding.
Wait,
And
no.
you're just agreeing
No,
with me
'cause the
because I said,
negative 4
isn't this true? I need y'all to be yourself.
No.
No.
Really? One times 10 to the negative 2 would be 2.0, correct? And I'll try to write farther up on the board. Okay. So really, this belongs down here. Five times 10 to the negative third really belongs between 1 times 10 to the negative 2 and 1 times 10 to the negative 10, or the negative third. Right? So sometimes they'll ask you what's the pH of something, and it's not going to be a pretty number, but you ought to be able to kind of think about it in your head and go, you know, what's going on kind of thing. So this number really belongs between these two, because the other way to write 1 times 10 to the negative 2 is 10 times 10 to the negative 3. So it goes 1 times 5 to the negative 3, 5 times 10 to the negative 3, 10 times 10 to the negative 3. Is really the mathematical thinking of it, right? As long as y'all can find that log button and find it, now you've got your second point on the AP exam. So far so good. Only 97 more. or 98.1. All right, let's see if you can go backwards. I'm going to give you a pH value, and you're going to find the hydronium ion concentration. So give me a number if you would. Anything between 0 and 14, but it has to have a decimal.
8.2.
8.2. So if the pH is 8.2, find me the hydrogen ion concentration, please, on your calculator. You made?
I got 6.0 times 10 to the negative 9.
6 times 10 to the negative 9. Everybody okay with that? Okay.
How do we find that?
Okay, so it depends on your calculator. So if I was using this Casio right here, I would hit, there's like 3 different ways to do it. So it's 10 to the negative pH. So on this one, it's got a button that says log. So I'd find the thing right above it says 10 to the x. It's what's called an anti-log or inverse log. So I would push shift log. Oops, first I turn it on. Sorry, my bad. Shift log negative 8.2. And I got 6.3 on this one. So. If you have a TI anywhere in the room, has anybody got a Texas Instruments kind of a thing? You got that thing, it's called a circumflex. It looks like a hat. Yeah, no.
I think she was suggesting she wanted to see like the algebra maybe.
Oh no, sorry. I was just saying I didn't see the equation up there, so I was
Okay.
like trying to figure out how
Oh,
to
how
find
would you-
it.
yeah.
Like other than that, but yeah.
If
Not
you have-
for the 10 to the x.
Yeah, so you'd have a 10 to the x. Some of y'all might have a little hat, and that's, you would enter 10, little hat thing, negative 8.2. You would actually say 10 to this power.
This calculator's stupid.
All right, so does that seem reasonable so far? And then this is pretty easy. If I gave you 8.2 as the pH, could y'all find me the pOH? Just subtract it from 14. So let's go ahead and do that. If the pH is 8.2, let's try doing it without your calculator. If the pH is 8.2, what would be the pOH?
5.8.
5.8, something like that? Okay, good enough. All right. So this is just called law of logs of this sucker right here. So these two come out, it's just law of logs applied to a thing for those of you who may remember that kind of thing. But this is only true at 25 degrees. Okay, so let's hurt your head just a little bit. pH of water, 7. One of y'all said that, 7, or he said 7 is neutral, and water is neutral. Water is neutral because for every hydrogen ion, there's a hydroxide ion, what we call amphoteric. It can throw out an H or an OH, an acid or a base. All right? But the pH of water at 30 degrees is 6.92.
The H concentration and OH concentration are still equal.
Ah, you are one smart cookie. Right? Because people will go, oh, that means hot water is acidic. No, it's not. Hot water is not acidic. Hot water is just, we've changed the K value because we heated it up. The amount of hydrogen ion and hydroxide ion is still exactly the same. Right? So here's the equation for how we do that, right? You take water and you split it apart into hydrogen ions and hydroxide ions, right? And so if the pH of water is 6.92, then the pOH is also 6.92, right? Because they would be the same values for water, right? Now, if we look at it, what happens as temperature increases? Don't look at pH. What happens to the value of K as temperature increases? it gets bigger, right? And what did we say happens when K gets bigger? What does that tell you about the reaction?
There's more products.
There's more products. So which one of these is true? As temperature goes up, we get more products. This one is the endothermic version. This one is the exothermic version.
Should be endothermic?
Should be this one?
No, it should
The
be-
bottom.
I'm not saying right or wrong. I'm just saying.
I think it's the
Y'all really need to stand by your convictions if you think that's right. Because it's got to be one of these two, right? So let's go back one more time. As temperature increases, we get more and more products. So think about equilibrium situations. If we add more energy, because we're increasing the temperature, when you add something to one side, it shifts towards the other side. So breaking water apart is actually an endothermic process. But you already knew that. Because what does it take to break bonds?
Yeah, energy in.
Energy. So to break water apart, it takes energy. It's an endothermic process. Right? So as the temperature goes up, the pH actually goes down. Doesn't make it more acidic. Just tells us something about the equilibrium. Right?
So, because our pH scale is 0 to 14,
At 25 degrees.
and they're in equilibrium,
Uh-huh.
6.14 and 6.14 doesn't equal 14. So does the scale change?
Correct. So if we go back to that list of calculations, pH and pOH add up to be 25 degrees, 14 at 25 degrees. So it's always stipulated as to when that's true.
Okay.
Right. Now, does anybody have a pool or something where they
I was going to say, this is my hot tub problem.
Right? Well, so if you have a pH meter at all that you stick into something, it automatically does the math for you. Because you think that pH goes from 0 to 14 all the time. And so when it calculates the pH, it also measures the temperature and does some quick math on it and gives you a number that you would find meaning for. I can't tell you what's wrong with your hot tub, so. All right.
They've done some calculations with it, like how much energy it requires and stuff like that.
Y'all ever seen a salt that is acidic or basic? A salt is just a metal and a non-metal, right? So, you ever seen a salt that's acidic or basic? Usually not by this point, because you're like, a salt doesn't have an H on it, right? So, let's think about how would you figure out whether a salt, a metal and a non-metal, whether they are make it like an acidic quality. I'm not saying how acidic, just acidic or basic. So the technique is we're going to take an H and drop it in front of the ions. So if I tell you chloride ion, you're going to drop an H in front and think about HCl. Put an OH behind all the metals, the cations. So if I said iron, I want you to think of iron hydroxide. So far so good? Okay. So let's do NaCl. NaCl, sodium chloride. So we put an H in front of the chloride. What do you know about HCl? Strong or weak?
Strong acid.
Strong acids. What do you know about the conjugate of a strong acid?
Worthless.
It's worthless. So since chloride came from a strong acid, it does nothing. Easy enough? Sodium. Pop a sodium in front of the hydroxide. We haven't talked about bases. Let's talk about what are the strong bases.
Sodium
Right?
hydroxide.
You had a list of strong acids. Let's throw in a couple strong bases. Can you all think of a base that scares you to death?
Sodium hydroxide. Strong.
Sodium hydroxide. So sodium. And the easiest way for y'all to think about this is group 1 hydroxides. So lithium, sodium, potassium, rubidium, cesium, francium, if you can get your hands on it. But all the group 1 hydroxides tend to be very, very strong hydroxides. And thus strong bases. So those Kb values, because B is for base, those Kb values are going to be huge. Ammonia, NH3, Is that one of those strong bases we just talked about? Ammonia, NH3. Is it one of the strong bases we just talked about? Is it a group 1 hydroxide? No. Since it's not one of the strongs, what do you know about ammonia? It's weak. What can you tell me about acetate ion?
Oh, it's.
An acetate ion came from acetic acid, right? We pop an H in front. Acetic acid. That's a weak acid. Weak acids give off conjugates that do stuff. All right, so let's go back. We were doing sodium chloride. We already decided the chloride does nothing. Then we're coming in here. The sodium hydroxide is a strong base.
But does do something mean weak or strong?
Do something means it's going to have some effect on the pH, so it's strong enough for us to worry about. I wouldn't call it strong or weak. It just is going to have some effect on pH.
Not worthless.
If it's worthless, it'll do absolutely nothing to pH. So the sodium does nothing. The chloride does nothing. What is the pH of sodium chloride solution? If the sodium and the chloride do nothing, what's the pH of water? 7. It's almost as if the sodium and the chloride are worthless. They don't do jack. All right? Let's do the same thing, but this time with sodium nitrite, NaNO2. Sodium nitrite. So let's do the sodium trick. Sodium hydroxide. Is that a strong base? Sure. Strong bases. What do you know about the conjugate, the sodium ion?
Not worthless.
Strong bases give off worthless conjugates, right? So since sodium came from sodium hydroxide, since it's a strong base, it gives off sodium that does nothing. So the sodium won't be doing anything for pH. Drop an H in front of the NO2. HNO2. Is HNO2 one of your strong acids? No. If it's not strong, then by definition, it's got to be weak. So what do you know about weak acids? Their conjugates do something. So the sodium is going to do nothing for us. The nitrite ion is going to be slightly basic somehow. So a sodium nitrite solution is going to be a little bit basic, above 7. Can't tell you how far above 7, but I just know it's going to be kind of basic. So a second ago, he asked about hydrofluoric acid. Why is hydrofluoric acid not a strong acid? Because it didn't make the list of strong acids, right? So the HF bond is a super strong bond. The HF bond is super strong because it doesn't have very many layers of electrons. Fluorine does, which means those electrons are going to be strongly attracted to the fluorine. Since that bond is super strong, it's not going to break off that H very easily. Right? So that's why hydrofluoric acid is kind of a weak acid. It doesn't just get rid of the H. It holds on to it. Okay? So if you had salts, wow, that really did well. What happens if you have NaF? Well, the Na, we've already decided it does nothing. So the conjugate of the cation does nothing. It's neutral. F came from HF. HF is a weak acid, so that means the fluoride ion does something basic. It's going to make it slightly more than 7.0. NH4Cl. NH3 is the base. NH3 is the base. So that means NH4 is the conjugate of it. So a weak base, ammonia, NH3, becomes NH4, its conjugate. Weak bases give off what kinds of conjugates? They do something. So this conjugate of ammonia is going to do something a little bit acidic. Something. The chloride comes from HCl. HCl is a strong acid, so its conjugate does nothing. So ammonium chloride solution is actually going to be slightly acidic, a little bit less than 7. Can't tell you how much, but I can tell you that. And then if they mix them, you're screwed because you don't get a calculator on the multiple choice section. So they won't do that to you. How about that? Right? Okay. Titrations. Y'all did a titration before?
I think so.
In Unit 4, did you do
I think we did.
a redox titration or anything like that?
No, I think they just did problems.
Okay. So a titration is, can I borrow your water bottle? Cool.
I don't remember.
This is some unknown concentration of hydrochloric acid. I need to know what the concentration of hydrochloric acid is. So I pour a little bit out for my homies. And then it's 25 milliliters. I know I'm using that much of the hydrochloric acid. I pour into my burette, that thing, a base that I know the concentration of. So I know it's, give me a number. You're my number girl.
What kind of number?
Sure.
Molarity for the base.
17.
17. So it's 1.7 molar, because that's going to be really hard to get. So it's 1.7 molar. And what I can do is I can look at the burette and I can squeeze out sodium hydroxide until it turns colors. And that color is an indicator. It tells us, oh, by the way, you hit the point you were looking for. Right? So the math becomes this. The volume of the acid, 25 mils. Pour that out for your bottle. The molarity of the base, 1.7 molar. The volume of the base I got from my burette. And I can solve for the thing I don't know, the molarity of the acid. A titration is using something you know to figure out something you don't know, analytically. Y'all have chicken processing around here or no? Yeah?
Yeah.
Okay, so a lot of chicken processing places, they'll want to know the pH of things, and while you can stick a pH meter into a vat of goo and stuff, oftentimes it's just easier to titrate it. And so there are people that titrate like crazy just to figure out how much of something there is, right? Pool people who are looking for, or hot tub people, will often titrate how much chemical does it take to neutralize that much chemical that's going on.
What's our hypothetical volume of the base that we used?
So if the volume of the base, and I'll give you all a sample problem to do, we'll do that in a minute. But let's say we started at 35 milliliters and we went down to 27 milliliters. So y'all know if we started at 35 and went down to 27, we used 8 milliliters. Does that seem reasonable? So far so good? Okay. You just picked up like 3 more points on an FRQ. So now we're up to 5. So 5 out of 50 is pretty good. So, all right. So this seems reasonable so far, right? So the last thing I want to do is, how would you actually find the pH of a weak acid? Like, how would you actually find that? So when y'all worked equilibrium problems before, what kind of tables did you use? What were those tables y'all used to solve equilibrium problems?
Is it ice table?
An ice table, right? Some people call them rice tables. So I didn't, I, C, E, right? We're going to call this one. We started out with 0.1 molar acetic acid, because we're trying to keep the math easy for y'all. Sound okay so far? Yes. And if you have 0.1 molar of this, then you got 0 of this at the very beginning. All right. Now.
So you're deliberately doing under that equation.
Yeah, because
so
it's written up there. It's less work for me. Let's be honest.
I mean, I'm just pointing everybody's attention.
Okay. So this is acetic acid. We're going to find the pH of a 0.1 molar acetic acid solution. And the best part is we already wrote the Ka expression. So hey, less work for y'all and me. So we get to reuse stuff. By the way, most ingenious eraser I've ever seen in my life.
It works.
I've never seen it.
It works better than the actual erasers. Everybody's enamored by it.
And then you're ready to go down to Toomer's Corners. Decorate. So if you're that kind of a fan. All right. So, if that's our starting state, that's pretty easy. What comes next?
The change.
The change. See? Is it plus x or minus x?
It's gonna be
If all you have is reactant, and you ain't got no product at all,
only minus.
this has to be minus x. Because you can't go minus. What are y'all, Congress people? We're just going to debt. We got nothing, we'll take away some more. You can't do that in chemistry, right? So this has to be plus x, and this has to be plus x. Not bad so far, right? So this would be 0.1 minus x, x, and x. So far so good? All right. Now, I do have to tell you this story. I had a student once named Molly. It was a very long time ago. Molly said, "I don't like ice tables, Mr. Elegante. Can I do hot tables?" I was like, "Well, sell them to me. Let's see." She's like, "H, here's where we are, where we started." Okay. What's the O stand for, Molly? She's like, "Oh my gosh, something's changing." Hate to ask. T, ta-da! And then I said, "Molly, why do you want to use a hot table? Because if you use a hot table on the AP exam, those other teachers are just going to laugh at me." She's like, "Because I think I'm hot." You do whatever you want to, but when you get to the AP exam, it's got to be ice. You can't use hot tables because everyone's going to think you're crazy, right? So I get 1.8 times 10 to the negative fifth. Remember, I gave you all that number earlier. Wasn't that the number? Something like that? It doesn't really matter, right? Is equal to x times x over 0.1 minus x. Y'all remembering that from equilibrium? And again, if you don't, you got to be like, can you go over one more time? You look like you don't.
I don't know what's going on.
Okay, so we started out with 0.1. It went down by some factor x. It's not 2x or 3x or 4x or whatever, because this whole equation basically balances with ones.
Okay.
So this goes down by 1x, and if the reactants decrease, then the products increase.
Okay.
Plus x. So far, so good? Mm-hmm. So equilibrium is, we started at 0.1, it lost some amount. So at equilibrium, it's 0.1 minus whatever we got.
Okay.
This is x because we started with nothing. We went up by some factor x. And so at equilibrium, that means we got x.
Those are zeros. Okay, I thought those were particles. So then, okay, yes.
Yeah, those are zeros. Good.
Okay.
Okay.
Okay, cool.
That's good. And so I just substitute those values over here. Right?
Where's the 1.8 times?
That would be given to you as the Ka value of acetic acid.
Just made it up.
Right? So, because we can't have you solve for everything. We got to give you some value. So 1.8 would be given to you. That's the Ka value. We know it's a weak acid. Now here's the problem. This is going to be a quadratic equation. This is going to be x squared and a 0.1 minus x, and this is going to be a lot of math. Now, does anybody's calculator have the fanciness? Yours does. Does anybody else's calculator have the fanciness to solve the quadratic without you even knowing what the quadratic equation is? Yours is fancy enough, whether you know it or not, to have something on there called the solver. You can just type in the equation, and it'll give you an answer. Just like you use the quadratic. And you don't have to know at all in the world what's going on. There's a YouTube video somewhere that shows you how to use that. Now, here's the thing. This calculator is approximately $8. This calculator is a lot more. Should the person on the AP exam with more money make a better score? Because of that, they're not going to penalize you because you have a cheaper calculator. So, remember, we said this number is incredibly small. How much of it turns into product?
A little.
Very
Approximately
tiny
0.
amount. So if you started out with, let's say you're Bill Gates, you started out with $10 billion and you dropped $5. How much of a difference to you is that?
Negligible.
But let's say you had no money. You're teenagers, you know what that's like. You're a teacher, you know what that's like. If you have $0 and you find a $5 bill, does that make a big difference to you? That's an infinite percent change. You went from 0 to 5. That's a huge change to you. So here's what we get to do for acid-base equilibrium. 0.1 minus something really tiny is 2 strips of bacon, 0.1. 0.1 minus a very small change is pretty much the same thing as 0.1. You'll see it as neglect the x or make the assumption. So 0.1 minus a very small change is still 0.1 by the time you do sig figs and everything else. So if I'm worried about weight and I stopped and got a Jack's chicken sandwich, a solid sugar Coke, and some fries and ate them before y'all got here, and I'm worried about weight, can I pluck out one nose hair and lose weight? Excuse me, if I pluck one nose hair and throw it on the floor, have I lost weight? Yes, I have. You can also lose weight just by breathing out. You weigh less. Not enough to matter.
Or
And
measure.
you can't continue to lose weight by breathing out rapidly. That will make you dead. Right? So, what does this make the math any easier? If instead of 0.1 minus x, we just drop in 0.1.
Yeah, just take the square root of the product.
Right? So if I do the math, I get that this is 1.8 times 10 to the negative 6th is equal to x squared. Did y'all buy that math so far? Okay, so let's find the square root of that number. What's the square root of 1.8 times 10 to the negative 6th?
I think 1.3 times 10 to the negative 3.
1.3 times 10 to the negative 3. Is that what everybody's getting? All right, now, let's see how that helps us. What does x represent in our ice tables?
How much? The concentration.
The concentration of the hydrogen ion, right? Well, if the concentration of the hydrogen ion is 1.3 times 10 to the negative 3rd, can y'all find the pH?
Negative log times that.
Because pH is the negative log of the hydrogen ion concentration. So let's go ahead and do that. Let's find the negative log of the value of x.
I didn't notice that you changed that exponent to -6. Okay, so you did divide. You did.
Well, I
multiply.
multiplied 0.1 times that and brought it to 10 to the negative 6th.
What other psychopaths are here?
Maybe bio.
From 2 to 4.
AP biology.
All right? So what'd y'all get?
Oh, I didn't do it.
2.9. So the pH of that solution is 2.9. Seem reasonable so far? Okay. Let's take a stab at a couple problems, just for funsies. All right, so I'll throw them up here and we'll see if we can figure them out together. So these are all the FRQs from 2014 on that have anything to do with acid base. There's a lot of them.
Are you all seeing a similarity in that math from equilibrium? Hmm. Morgan?
I just don't remember.
You don't remember? It's just, he just used that K expression right there. The concentration of the products over the reactants.
Yes. Okay, I didn't know.
Yeah. That's why I was saying earlier, like he did that ice table under that equation because he's referring to it. Then he did the math under that K constant expression because he's referring to those values. That's what we solve for is the concentration in that
I
equation.
knew that. I thought you were just asking about like in general related to equilibrium. I was like, I don't know what you're
Oh,
asking.
okay.
In general, for equilibrium, we write down our initial quantities, whatever they are. We use Q to figure out which way it's going to go. If it's greater than K or less than K, is it going to shift to the right or to the left or whatever like that. And we come up with these values, and they usually give you like a K number, right? Or they'll give you all these values, and they ask you to find a K number. But basically, an equilibrium expression has usually got 1, 2, like 4 parts. They have to give you 3. And mathematically, you find that 4th. All right, so let's blow this up just a little bit more, and we'll see if we can answer any part of this question. All right. So here's, can y'all see that back there? Yes? Okay. Because my eyes could not see that at 55. So identify one of the conjugate acid-base pairs. So y'all turn and talk to each other real quick and see if you can go ahead and figure out one of the acid-base pairs.
Base, conjugate acid.
No, I don't think so. Because it's not. Oh wait, no, I wrote that wrong. It could. No, never mind.
Well, the water one's easy, right? Because it accepted a proton. So it must have been the base so that on the other side, it's the conjugate acid. The other one lost the hydrogen, so it was an acid. So on the other side, it's the conjugate base.
So does anybody want to share their answer? You moved your wrist, so I took that as a hand raise.
I think we said HClO and ClO negative.
Right. Identify on the AP exam means write it down and stop. No need to explain or anything like that. This and that. You didn't even have to label which one's an acid, which one's a base. 1 point. That's the first point you all earned earlier. Right?
Okay.
Let's see if they gave you enough information. Well, no. It's not this one.
I think part of the question's running off, though.
Yeah. All right. The student is given a solution of phenol red of unknown concentration. No one cares. Solutions of phenol red are bright pink under basic conditions. All right. They use a pH probe, and the pH is 11.2. Can you calculate the hydrogen ion concentration? Give that a stab. The pH is 11.20. Keep in mind, if this was a sig fig question, only things to the right of the decimal count as significant figures. So the number as written, 11.20, is only 2 sig figs. Everything that comes before the decimal point has to do with the exponent.
10 raised to the pH, right? That was clever. I think you may be right.
10 to the negative pH.
How did you do it on this calculator? You know, there's a stupid button, but it don't 11.2.
I think it's broken calculator.
Maybe you can figure out how to do 10 to the pH on this one.
Do you usually use one of these? Because I think one of them was in that box today.
So, for anybody who has these fanciness, I would just enter the 11.2 and make it negative, and I'd push that second log button. Second log is 10 to the x. And I got 6.3 times 10 to the negative 12. So, enter the number, flip it to negative, then hit the second log button. All right, 6.3 times 10 to the negative 12. Sound reasonable? That's pretty good. All right, let's see what other things they might have in store for us. Here's a good one. Methanoic acid, which you don't have to know even what that is. One of your organic acids. Ionizes according to the equation above. Write the expression, the Ka for the reaction. And I'm going to go ahead and give y'all the job of finding the pH of that, if you would, as well. So let's go ahead and write the expression Ka, and then let's go ahead and find the pH of a, what's your name again? Gracie, give me another number less than 1.
0.53.
Okay. All right, Gracie called 0.53. So we need to know. So we need to know the pH of a 0.53 molar methanoic acid solution. So go ahead and write the Ka expression first, and then work together is what I prefer y'all do. Go ahead, take the equation as written, go ahead and build yourself an ice table. Go ahead and do that, sucker. And go ahead, the initial concentration is 0.53. And go ahead and work to see if you can find a pH. Remember, if you don't know how to write a Ka expression, remember that's on your reference sheet. It tells you how to write a Ka expression. Products of a reactant, right? And if it feels like we're going fast, it does. Because we are.
For writing an expression, do we have to fill in the concentrations or just?
An expression is just where you write Ka is equal to a bunch of letters. You should never put a number there unless it's an exponent. It's like a mathematical computation. Or like a mathematical formula, sorry. So in that case, it wouldn't be,
Just be Ka.
so it'd be Ka is equal to, it would be H plus, but where you wrote A minus, it would be that negative ion right here. So it'd be this sucker right here,
Yes, sir.
the methanoate, and the bottom would be the HCOOH.
Thank you.
You ought to be able to, once you get the expression, you ought to be able to write yourself an ice table. And I would really encourage y'all to work together. Hey, is this what you got, kind of a thing?
Oh, never mind. I'm just gonna do that.
I'm laughing at that because he knows it.
Remember, every ice table gets set up underneath the equation. So you kind of need to copy down that equation to build your ice table underneath it. if I give you nothing but the HCOOH,
I thought you said that.
then you're zero.
Right, I just kind of, I skipped over it, because I just figured it was always gonna be there.
Nope.
Okay,
So you can't assume that if it's 0.53, that the other one's gonna be 0.53. Because here's what you're assuming. You're saying all of the reactant is going to become a product.
okay.
But we know that this is a weak acid because the Ka value is pretty small. It's less than 1. So we're trying to figure out of that 0.53, how much of it is actually going to turn into product. So instead of, this is gonna be 0 plus X. So this is gonna be X, and this is gonna be X. You can't assume that they're 0.53. Unless the K was very large. If the K was very large, like hydrochloric acid, if it's 0.3 molar, all of it will turn into hydrogen ion.
But we just found,
And part of this I'm showing for y'all.
we just found.
This would just be X and
Any
X,
hydrogen.
because 0 plus X plus X.
It's just like the one we did, I think,
Just to remind you that it's, that one's going up by some factor of X. So you ought to be able to substitute your X's
So this is a kind of.
and your 0.53 minus X's into your expression.
I guess it's the hydrogen ion because he took this chemical bond.
Because that's what X
Okay,
is.
so you did that times that, yeah. Mhm. And we're gonna assume that 0.53 minus X
This should
is
be
0.53. Because no one wants to do the funky math, even with the fancy calculator, right? So you'd want to write underneath it
Which
that,
is-
that's two strips of bacon, 0.53. You're trying to show the reader,
Just taking
hey,
the square root of
it's
0.53.
about 0.53.
So
So, I'm sorry, I'm gonna divide the K by
So
0.53
X,
and take square
therefore,
root.
And that is. the
X
concentrate.
is your H3O ion.
Because the minus X is gonna be insignificant, right? So now I have X
So
squared
now that you know the H3O
over
ion,
0.53 is equal to
how would you
1.8 times 10 to the whatever.
H if you know that that is the the negative log of that?
Yeah.
Negative log of-
No, but that's right, that's right. You did it. It's the
Yes,
same thing.
it's confusing, it
It
seems
is.
pointless.
Well, it's not when, so we established this back in equilibrium, because there was and he said it. There's two ways that this problem can be
Just
set
say
up.
2.
One, this is an easy version because we're starting at an initial concentration of 0. The reaction hasn't gone. But if the reaction has been going for some time, you can't do it without ice table.
Are we ever gonna do that in anything? Or like on the?
Oh, no, that'd be a good question to ask him.
What's that?
So we're talking about, like, we're starting the reaction at 0. In a situation where the reaction has already proceeded to some extent and we know a concentration of a product, she was asking, is this would you see a question like this on an open-ended?
Well,
Yes.
okay.
You're reading into 10 minutes.
Okay.
Okay, and we want to call that 0.53, I mean, it's going to be 2. So we would want to have 2 decimals.
What'd you get?
In our answer, because the only sig figs
I did
in a
something
log
wrong.
basis are to the right.
I did something wrong.
So you want to call that 2.01.
Well,
That's what I got for the H plus concentration, that's not what I got for the, oh wait, no, it's the same thing. I have no idea. No, it's- That's the H plus.
So also I got for X is equal to X squared. And I'm taking the
All right,
square root
now.
of this.
The question is, how weak does this have to be
1.8.
before you can neglect the X or make that assumption? How big or small can that be, and yet we still say 0.53 minus X is the same thing as 0.53? Is there ever a time when we can go like, oop, can't do that anymore? Yes, and here's the general rule. I'll say it twice. First time you hear it, second time you write it down. If your K value is at least 10 to the third away from your initial value. So look at this, 0.53 and 10 to the negative fourth. Well, this is 5.3 times 10 to the negative 1. This is times 10 to the negative fourth. Is that at least 10 to the third away? Then you're safe to make the assumption.
Yeah.
If you're at least 10 to the third away from your K value to your initial concentration, you can feel free to do the cheater math. If you're not, you can't do that anymore. It'd be more like me with $50 losing $5. That means something to me, right? That's a couple things off the dollar menu, or the value menu. I don't know why this thing keeps doing that. I mean, I'm plugged in. I'm charging. No, I think it's coming back. It'll come back.
Cheater math is what you're referring to is you can assume that the change in the initial is approximately 0.
Correct. It's not enough to matter. And for anybody who likes the quadratic formula and likes to work the math on that, or you have the TI 84 plus silver calculator that does all the fancy math, you can plop that into the solver and it'll give you a value for X that's going to be slightly different. But it's not enough to map.
So what is our pH? Did you?
Everybody's getting 2.01. 2.01. Is that what y'all got for pHs?
Finished it.
I got,
Oh, okay.
I did not. I got 1.8. I don't know what I did.
What'd y'all get for a value of X? Let's back up the process.
9.77 times 10 to the negative.
Oh, maybe it's because I didn't do
9.77 times 10 to the negative 3 is what they got for the value of X. That's about what you got, right? And then if we take the negative log of that. So.
Yeah, I didn't do the negative log. That's
Okay.
So are we finding the pH of the acid to start with?
We're finding the pH of the solution,
Okay.
which is 0.53 molar methanoic acid.
Okay.
So y'all tend to think of there's a weird world of products and reactants, and you can find the pH of one and not the other. It is the thing.
1 point.
Like oftentimes y'all will be like, I'll heat up the reactants. You can't heat up just reactants.
Yeah.
You're heating up a pot of stuff, right? So we're finding the pH of this solution.
Okay.
Now, what if I had told you to find the pH of 0.53 molar perchloric acid?
Just divided by 0.53.
There's no need to do an ice table
Yeah, I think it was
because how much of a strong acid turns into ions?
1.8 times 10 to the negative 4.
All of it.
It's good. Divided
So if
by-
I give you 0.53 molar HClO4,
You get this number.
what's going to be the concentration of the hydrogen ion?
Something.
0.53. So finding the pH of a strong acid is easy peasy. You just take the negative log of 0.53
That,
Okay.
you get something.
because all of it turns into ions.
Negative log of that is this.
Because remember what the Ka for HClO4 was?
Large.
Large. Right? So far, so good? Okay, one more thing to show you, and then we'll let you stand up and stretch, go to the bathroom if you need to. Because we're getting close to the time where y'all will stop listening. Because I stopped listening just a second ago. All right, can y'all pick an indicator? Which indicator is best, right? Well, depends on where the equivalence point is. Now, the equivalence point is where all the acid has been used up by all the base. So in other words, you've added enough base to get rid of all the acid. So you had your burette, and you dripped, 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 dripped. As soon as you added enough base to get rid of all the acid, we call that the end point or the equivalence point. That kind of makes sense? That's the end of our titration? Okay. So let's say that your end point was 7. Would methyl violet be a good choice for something that ended at a pH of 7?
No.
It changes color down here at 1 point something. Not a good choice. How about alizarin yellow? Would alizarin yellow be a good choice for something that had an equivalence point of about 7? It's not going to change colors till almost 11 and a half. So what do y'all think would be a good choice for an indicator that would change at somewhere around 7?
Phenol red.
All of y'all do the same thing. I have to do the same thing. Okay, somebody said bromothymol blue. Okay.
Phenol red.
Methyl red. Methyl red is going to kick right about 6. So that's going to be a little
Phenol red.
early.
She said phenol red.
Phenol red. Phenol red's going to start to change about 8 point something. So it's going to actually change color just a little late. I mean, phenol red would work. Phenolphthalein is the one most people use in a high school or college thing because it's cheap. And it turns from colorless to a bright magenta or pink color. It's great, right? Even though it kicks it around 8, it's still a good choice just because of the chemicals. But you need to be able to pick one, right? And I'll come back to this in just a minute. So let's look and see what a titration curve is, okay? So can y'all go ahead and kind of doodle this on your notes somewhere? Doodle the whole thing. And if you want to, as they get closer to the AP exam, there's actually some stuff on Canvas where there's some particulate models that tie to these titration curves where they kind of have to pick out what's what. That'd be a good review for them. There's also a whole packet on titration curves if they get excited about it.
Excuse me.
Okay, the blue one doesn't disappear. The blue one becomes the same thing as the red one. That's why it looks like that. Right. We're still drawing, sorry. There's some hallmarks I'm going to need y'all to find, so be looking at it for a second, be thinking about this. Find the point on the x-axis where the graph goes vertical. So look for the graph where it starts zooming skyward, and find the value on the x-axis. So find the part of the graph where it goes vertical, and find that x-axis value. And what would y'all say the x-axis value is? 25 milliliters. So where it goes vertical, that tells you how much of the base it took to get to the equivalence point. So the point where it starts to go vertical tells you, aha, I hit the magic amount of base or acid or whatever it takes to get to the equivalence point. So our equivalence point, it took us 25 milliliters to get here. So far so good? Because it's right there. All right, here's the other thing I want you to find. Take the red curve up top and the red curve down at the bottom. The part where it goes vertical, find me the midpoint of this line. What is the y value of the midpoint of where the red goes vertical?
It looks like 7 to me.
Would y'all say 7? Okay, so go ahead and make a mark there, right here, that says that is the equivalence point. The equivalence point is right there at a pH of 7 and an X value of 25. So this point right here is the equivalence point for the strong acid. Try to do the same thing for the blue line. Try to find the midpoint of where the blue line starts to go vertical
I'll say 9.
Remember, the blue and the red are the same line up here. So, what is the pH value at the midpoint for the weak acid line?
Y'all's is not colored, so you may want to label the line strong, weak, like that.
9? Okay, let's see. I can live with 9, sure. So I would say right in here, that is the equivalence point of the weak acid. All right, now, you got those two thing labels. Let me tell you what's going on. This point right here at the beginning of the graph, this is all acid. The only thing you have in the container is acid. You haven't added any base yet because it's at 0. So this is all acid. At the equivalence point, you've gotten rid of all the acid. At the equivalence point, you've turned all of the acid into its conjugate. So this was hydrochloric acid. All of it's HCl. Up here, it's all now just chloride ion. Well, strong acids give off what kind of conjugate? Not weak, stop it.
Worthless.
Worthless. So, what's the pH at the equivalence point? 7, because it's a worthless conjugate. Weak acids give off a conjugate that does something. So this is all acid. This point is all conjugate base. So at the beginning, all acid. At this point, all conjugate base. Why is the pH greater than 7?
Because they do something.
Because the conjugate does something. Now I'm going to ask y'all a very tricky question. If this is all acid and this is all conjugate base, what's true halfway there?
You have equal concentration of acid and base, or conjugate base.
You have an equal amount of acid and conjugate base. Why is that? You've used up half of it. So half of it has turned into conjugate base, and the other half is still the acid. Does that seem reasonable? Okay. So some hallmarks I want y'all to be able to pick apart. Strong acids start really low because strong acids have a very low pH. Strong acids give off lots of ions. So strong acids are going to tend to start way down low. Weak acids are going to have a little bit of a swoop. They have a little bit of a swoop that goes up just a little bit. So if you're trying to identify, is it a strong or weak acid, whatever's going on. Strong acids start straight. Weak acids start swoop and a little bit higher. So far so good? Okay. So let me show y'all a couple and you can tell me, I am so bad about leaving this stupid thing around. All right, so y'all tell me, what did we start out with in the beaker this time? Did we start out with an acid or a base?
Base.
A base, because we're way up high. Was it a weak base or a strong base?
Is it a weak because of the
Weak base because of the, say it,
swoop?
Whoop.
swoop. Yeah, it's got a little bit of a swoop, so it's a weak base. Notice, you don't even have really numbers in here, so it's really hard to tell. But that's a little bit of a swoop. What point tells you the equivalence point?
C.
No, not in Spanish. What point, no, I'm sorry, bad joke. So, point C is the equivalence point. What's our other proof that this was indeed a weak base?
Because you're getting off a strong acid.
Don't
No,
say
the equivalence
strong.
point is lower than 7.
Avoid saying strong. Weak bases give off conjugate acids that
does something.
do something. When y'all say strong, you tend to think, eats my flesh off. So, Weak bases give off a conjugate that does something. That's why our pH is less than 7. So this could have been ammonia turning into ammonium, the delicious polyatomic ion, ammonium. Right? What is B? Why is B important?
That's the halfway point.
That's where it's half base, still left, and half of it has been turned into conjugate acid. So what would you call something that's halfway to the equivalence point?
Like the midpoint?
Yeah, but a better word for that, that's halfway to the equivalence point. How about the half equivalence point? Everybody okay with half equivalence point? Okay. Let's see if we can show you this one. What is the pH at the half equivalence point?
5 point something.
Okay, 5.4. So how many milliliters did it take for us to get to the equivalence point on this one? No, to the equivalence point, not the half equivalence.
22.
22. Okay, so the half equivalence point is going to be half of that much. So about 11 milliliters. So what is the pH at 11 milliliters? 5.5, 5.4, something like that. Sound reasonable so far? Okay. Y'all take a moment, stand up and breathe and things like that. I'm going to give you a slightly different problem with acetic acid. Okay? Give you a slightly different, stand up, move, get your brain moving. We're going to do a slightly different acetic acid calculation.
He made someone do that, not your class. But it happened.
You know the funny thing about coconut water? There are not enough coconuts on the planet to produce the volume of coconut water that we sell in stores. Oh, most people are lying. Because how would you know?
But that says 100% pure.
Yeah, 100% pure, whatever it is. but-
He watched the Hawaiians actually squeeze.
Right, coconut water became one of those, everybody's got to have it, and all of a sudden there's more. Kind of like very expensive wine. At some point, there were like 200 cases of this very expensive wine sold in one year. And when you look back at the historical records, they only made 10 that year.
Are you familiar with that guy who he had some ridiculous palate or ability to detect the different things in wine, and he was making them in his
Oh, yeah.
basement and selling them for millions of dollars?
Yeah, they would go to restaurants and steal that wine bottle with that label on it that they'd thrown out in the trash, and he would take it and put cheap wine in it and then resell it for tons and tons of money. Because if you have a really expensive bottle of wine, guess when you're going to drink it? Never, because it's really expensive. And so no one's ever going to know. So now fancy restaurants take those bottles and they break them. And for the very, very expensive old wines, the way we tell whether or not they're real or not is we look for nuclear isotopes in the wine. Because ever since we've been blowing up nuclear stuff on the planet, there's a little bit of nuclear stuff in pretty much everything we touch, eat, and drink, that kind of thing. And if they made that wine in 1880, there shouldn't be any kind of nuclear stuff in it. So that's usually how they tell.
Yeah, Kodak had a real issue with this because it was ruining their film.
Oh, okay.
The testing in Los Alamos or whatever, or wherever it was in Mexico, they were picking it up in their film.
All right, this time I'm just going to do a little bit different. Okay, last time we started with 0.1 molar and 0 and 0. This time I want to give you just a little bit different situation. Instead of starting with 0.1 molar acetic acid, I also want you to have 0.1 molar of the acetate ion. So go ahead and start with some of the acetic acid and some of the acetate. Just do an ice table one more time, where you have 0.1 molar of each one. And just as a reminder, the Ka value is still right over here. So this still works.
Is that out of
I just heard running footsteps. That's a man excited about some chemistry.
He's excited about something.
So go ahead and give the ice table another run, except this time instead of starting with just acid, start with 0.1 molar of the acid and 0.1 molar of the acetate. Go ahead and do an ice table for it again. Same value, 1.8 times 10 to the negative fifth for the Ka. This is the thing I fight with teachers most about is they should never say, now we're going to cover buffers. Because the kids see it as, oh, I heard that's hard. And because the teachers, when it's the same problem. You just, it's a mixture of the two. So if we try to never scare them off. It'd still be plus X on the right. Because you got 0 of the H3O. So since you got 0 of that one product, the only way it can go is to the right. So it'll still be minus X, plus X, plus X.
Am I able to make this same assumption that this is approximating 0?
Yes.
So is it not just? Okay.
I mean, if you want to do the math the other way, you can. And in colleges, they still have them doing the quadratic and stuff.
Yeah, because they got to make it hard.
Well, and in truth, chemists nowadays are just dropping in a computer, and the computer does the
Yeah.
calculations.
Yes, I think so.
So remember, you had 0.1.
And then, yeah.
Goes with that.
I got it.
Do me a favor. When you get all this stuff in
So
here,
whenever you
Go
get
to
these
this,
concentrations in the
and plug your stuff in.
you multiply them together. So is it like distributing this to
Okay.
the?
Yeah, but no one wants to do this math, because that already looks
Yeah.
scary. So this is where we're gonna do that, make the assumption.
This,
Okay.
So if you start out at
Go in there,
0.1
yeah.
and you go up by some
This,
little amount.
go in there,
it's the
yeah.
same good point.
it's cancel.
Okay.
So we're gonna
That's
say
X.
that 0.1 plus X. pretty
This,
much 0.1.
go in there.
0.1 minus
Just
X.
that is equal to X.
I mean, you can do that, man. And there's actually a website you can type that kind of mess into for your fancy songs, and it'll do the math.
Yeah, you probably could tell Excel to do it.
Sometimes when I'm helping people, I just pull up Google and type in the the equation as written. They're like, oh, you didn't have to use the quadratic. I was like, I don't remember the quadratic. I know it's negative b.
Yeah, I don't remember much.
That's pretty much all I got.
So you say that that's like
So then-
ignorable as well? the plus
Yeah,
X?
correct. Because if you're at 0.1 and you go up by some tiny amount, it's pretty much me. Unless you like.
I like
math.
the thousandth rule of thumb too, because you can glance and be like, okay, this is, they're
Well,
not.
the book,
you know,
the books
1,000.
give the 95% rule.
Oh, yeah, okay, so
But
that's
in
how I
order
was
to,
taught.
yeah, but in order to do the 95% rule, you have to solve it using the quadratic and then decide whether or not you're that close. And then you, but they
I
should
did the
never
ice
run into a
table,
point
I
on the
added
AP
a step,
exam
so I
where they have to use the quadratic
see,
simply
like-
because of calculator cost.
Yeah.
This is
In
the
fact,
answer.
in biology,
I
they
don't
have
know
a
the
section,
answer.
use a calculator, they have to use a full
So we're
function.
finding what X is, so
They
we're
can't
only finding the concentration
have
of
anything that
X.
stores information, so.
What is it now? What was you saying?
Because that's the
Okay, so X
She asked
is,
if I did an ice table, I said.
Okay, so
yeah,
how would you find
one
the
of us
pH?
added a step, so
if
I
you
had-
knew
I
that
just
that
wrote
was the
everything.
concentration?
Yeah.
So this is what X is, so it's the concentration
You can make the judgment that this is,
So to find the
they're
pH.
different by 1,000.
Right.
Because like on that last one that we were talking about, I was just like, oh, I'm just gonna take the square root of that thing.
Yeah.
Yeah, don't.
So the thing, like, my time.
So you would not
my
do x
issue
squared.
on tests is not finishing.
This would end
So
up being
if I'm doing anything extra, I need to know. So I really need to just like
is equal to the value of K.
figure out if it's weak
So
or not.
you should never have something
Then
where you're
if it's not,
doing
not
it
good
extra.
at
I think
So
it
you shouldn't have to do a
times
square
10 to the negative fourth, and then your concentration is close to 1, then that's probably a pretty good, safe bet. One thing you could do to build up like the algorithm or the efficiency of it is just work a bunch of these kind of problems.
What do we get for a pH?
Oh, I didn't do that part yet.
I mean, you've got X, and X is our concentration. So let's go ahead and find it.
It's just negative log of the concentration, okay.
Can't be 1. Okay, so you just did the opposite. So you did 10 to the negative value of pH.
That's my point at Tate left.
And you're supposed to be taking the negative
3.7, is that what you got?
right there. So you did it the wrong way. You did an anti-log, you get this.
Do you have an answer?
I based on, what'd y'all get?
Oh, we're getting 4.7.
Sure. Something like
That's
that.
what I got.
You'll notice I'm the laziest teacher there is, because if y'all can do the work.
Am I not doing my calculator right?
Yeah.
So this is finding the pH.
No, it
based
comes
on
to the negative fifth.
This
What'd you do?
hydrogen.
Negative fifth? Oh, well, crap. I just read it.
Hydrogen.
Okay. Because of 1.7, I was like, what did I do wrong?
So there's no hydrogen over here, because that hydrogen is stuck to the.
Where's Jaden?
She's helping her dad with their
The
house.
boyfriend, girlfriend you see in the hallway are always together and never apart. Then finally, that's you, sorry.
This is-
They're always like, why do those people always have to be together? You know, so, it's not hydrogen bound.
Teach this, because I'm not gonna have time to
Because we're trying to describe how much
go into a lot of
of
detail
that
on that.
hydrogen atom is coming as a strip.
Get for the pH.
4.7?
All right. Do y'all remember the pH of a 0.1 molar solution of acetic acid? Remember that first pH we found?
It was like,
Was it?
2.9. Something like that, 2.9. Are you telling me that because this time we had some conjugate base that the pH should be higher? If I gave you some of the conjugate base, shouldn't the pH kind of go higher? Well, that makes sense. When you add a base, the pH goes higher. So what was the pH y'all found this to be? When y'all solved this problem and found pH, what did you get for a value? 4.7? So we're close. Now, that means that that half of the acid has been turned into conjugate base. So here's a little cheater diagram. That is not what I wanted. Where is it? All right. This is my fault for not having this. All right. What did we call this thing that we said, what did we call this thing right here? Half equivalence point. So can y'all label on your little graph, this one back here, the red one? Can y'all label the half equivalence point? And can you write something very special? At the half equivalence point, we're going to say that pH is equal to pKa. So at the half equivalence point, the pH is equal to the pKa. At the half equivalence point of a weak acid, the pH is going to be equal to the pKa. Now, how does one find a pKa? You take the negative log of Ka. take the negative log of Ka. So at the half equivalence point for anything weak, pH is equal to pKa. Very important point. You would not believe how many points you can get on the AP exam just by knowing that fact.
In terms of seeing the problem and being able to solve it quickly, or this is a question in particular?
Well, they just know that students struggle with calculators sometimes, so oftentimes they will give them graphs and numbers and things that allow them to easily extract an answer. And we'll show you a couple. All right, now, would y'all agree that this is a mixture of acid and its conjugate base?
Yeah.
Okay.
Yes.
Have y'all ever heard of buffers before? I notice y'all have a health academy down here. Has anybody taken any of those classes? Okay. There's a thing in your body called the bicarbonate buffer system, right? So a buffer is something that maintains a constant pH, or it lets the pH change very little. A buffer is something that pH changes very little.
Pretty sure that's what the baking soda in my hot tub does.
Yes. Baking soda can either, baking soda is hydrogen carbonate, HCO3. So you can either accept one more hydrogen, or you can give one away. If you've ever done electrophoresis of DNA, you squirted DNA in there and they hooked up electricity, that uses something called a trisphosphate buffer system. The buffer just helps the pH stay about constant, right? Okay. Y'all have probably seen something like this around here somewhere, shopping centers, neighborhoods.
Behind Chick-fil-A.
Behind Chick-fil-A. This is called a retention pond. What's the job of a retention pond?
To retain.
Its job is, when you have a storm, to not throw all that water in your lakes and streams and stuff like that. Where do you have to put a retention pond? Anywhere where you pave over the earth. Because when you pave over the earth, that earth is not going to absorb that water. It hits concrete, hits the roads, hits something, goes in lakes and streams, can cause flooding. So, a retention pond, its job is to accept the water sometimes, just like a base would, or you could also use it as a source of water. Right? You could go and get some water out here, or you could store water in there. Either way, this does both jobs. That's what a buffer is. A buffer is something that has an acid and a base component to it. So, let me give you something, and you tell me if this can be a buffer. If I gave you some hydrochloric acid and some chloride ion, could that be a buffer?
Like just hydrochloric acid?
No, I gave you a mixture of hydrochloric acid and also some chloride ion like sodium chloride. You're saying no. Isn't this an acid and its conjugate?
But that's a
base.
worthless base.
It's a worthless base. What do worthless things do? Nothing, right? So this can't be a buffer because it can't do that job, right? How about, let's see, lactic acid and lactate.
Probably better.
Is this a weak acid?
Mm-hmm.
Yes.
Because
It's not on the list of strong ones.
it ain't strong, and it's conjugate lactate. This could be a buffer. You've got a conjugate base that does something, whatever that is. We've got an acid that is an acid in some way. This could be a buffer. Okay, good.
So that's the reason why the baking soda works, is because it's a weak base, but its conjugate acid does something.
Right, it's weak to begin with, so its conjugate does something, right? So let's write down how we make a buffer. What does it take to make a buffer? We need a weak acid and its conjugate, or we need a weak base and its conjugate. That's the only way to make a buffer. So I can give you a weak acid like hydrofluoric, a weak acid, as long as I also give you some fluoride. right? It's conjugate. I can give you a weak base like ammonia, as long as I also give you some of its conjugate, ammonia. As long as there's some of each, this makes a buffer. Y'all understand the concept there? Okay. What do you notice about this buffer? Same picture.
It's given water.
Or it's got a lot in it.
It's got a lot in it. At this point, we're about to exceed the buffer in capacity or blow the buffer. Could this thing accept any more water? If it did, it looks like over here it's about to flow over the edge. So buffers have their limits, right? Buffers have their limits. So let's go back to this graph real quick. What's true right here?
It's
All weak acid.
all a base that can do something.
All conjugate base. Halfway,
It's equal conjugate base and acid.
equal conjugate base and acid. So far so good? Okay. Which one is in greater concentration here? The acid or the conjugate base? There's more acid than conjugate base. More conjugate base than acid, right? Because we passed the halfway point. So far so good? Notice what happens in the middle to the pH. Right here where you have a mixture of the acid and its conjugate base, what do you notice is true about the pH and the slope of the line?
Constant.
It's not quite constant, but
It's more.
it's changing very little. So this point, from here to here, we call that the area where it's a buffer, because that's a mixture. This is a mixture. This is a mixture. Why did it all of a sudden go up real quick?
You blew the buffer.
One got more than
It blew the buffer. Okay, so remember what I said my daughter had?
No.
Type 1 diabetes. Okay, so it's called diabetic ketoacidosis, meaning you make ketone bodies. Those ketone bodies have an acidic quality to them. So this was her 6 weeks before she went in the ICU. Her body was making acid. Her body said, I got this, I got a buffer. Used up some of the base. I got this, I can deal with more acid. I've still got some conjugate base. Still got some conjugate base. Still got some conjugate base. And then, right when she started to show symptoms, she went from having flu-like symptoms to being in a coma in about 4 hours because she exceeded her buffer.
Yeah, and it's a log function too, so it's,
Right. So what would you do if you were a doctor? She's obviously, her pH was low for a body. So what would you give her?
Base,
A base? What kind of base would you give her?
strong base?
A strong, how much would you give her?
I don't know.
If you give her a strong base, you're in danger of,
enough to get her to.
this is dead, this is dead, this is dead, right? So we don't want to give her too much. Can you titrate? Can you like open up her blood vessel and drip it from a burette and wait for it to turn pink from the indicator? Not when it's blood. It's kind of hard to see, right?
So weak acid?
Weak
Weak
a-
sorry, weak base, weak base.
Which weak base?
the one they tell you in medical school to use.
No. What's the name of the buffer system in your
The
bicarbonate
bicarbonate.
system? So the pharmacist walks in, gets a very fancy box of baking soda, one that's super pure, stirs it in water, and they give that to her in an IV. They reestablish the buffer. Everybody always wants to kill my daughter. No offense, but everybody wants a strong base, potassium hydroxide, right? So they just reestablished the buffer.
So the same thing is true, I think, for what you were mentioning earlier about you don't try to lose weight by breathing out too much, because losing too much CO2 shifts this buffer as well.
Right, when you lose too much CO2, your pH because you're driving the equilibrium the other way. Your pH gets out of whack, and y'all hyperventilate sometimes. That's your body's way of going, this idiot doesn't even know how to breathe. So when your pH starts to get out of whack because you hyperventilate, it hits reset, you know that button, you fall over, and you start to breathe normally again, because obviously you thinking about it is doing no good, because you're like, I can't stop breathing. Reboot, right? Now, that's a buffer. A buffer is a mixture. So far, so good. Yes? Okay. I want y'all to find this formula on your sheet. And this one right here.
You see it?
pH is equal to pKa plus log of, yours will say A minus over HA.
Okay, that's
Y'all with me so far? A minus is the conjugate, HA is the acid. Now, for those of you wondering where this came from, this is just law of logs from this equation up here. From the Ka expression that we've been using all over the place, this is called the Henderson-Hasselbalch equation. Not necessary that you know it. That is called the Henderson-Hasselbalch. Let's see if we can solve this problem right here without building an ice table. What was the concentration of the conjugate? 0.1. What was the concentration of the acid? 0.1. What's the log of 0.1 over 0.1?
0.
What's the log of 1? 0. So, at the halfway point, pH is equal to pKa. Now, let's say, oh my God, you just glued to myself. Let's say we're over here. Let's say there's more conjugate base than there is acid. That seem reasonable? Okay, let's see if y'all can solve this. So let's say that there's 0.3 of this and 0.1 of this. Let's say there's more conjugate base than acid. Can y'all solve that one? Go ahead. You know that the conjugate is 0.3. You know the acid is 0.1. Try to find the pH, not using an ice table, just using the Henderson-Hasselbalch.
And we're finding pH.
And you're finding pH. Because remember, Ka is always this. For our purposes today, the Ka is 1.8 times 10 to the negative 5.
Okay. But this is our pKa? That's our Ka.
That's our Ka.
pKa is negative log.
Oh, I got you.
Right, pKa is just the negative log of the Ka value.
Oh, I see what you're saying.
So my math is the log of 0.3 over 0.1, which is the log of 3. And if anybody gets an answer, let me know, because I'm far too lazy to do anything.
5.22
5.2
for pH, not
for pH, yes.
Yeah.
Yes.
5.2.
Yeah, that was close.
Anybody else get that?
That's partial.
Okay. All right, so let's go back at the picture and make sure that makes sense. Ooh, wait, too far. At the very beginning, the first problem you did, y'all said 2.9. At the halfway point, y'all said the pH was 4.7. Does it make sense that when there's more conjugate base, the pH should go up?
Yes.
Yes.
Because we've got more conjugate base. The conjugate base is 0.3, so the pH should have gone up. So did we go from 4.7 to 5.2?
Yes.
Yes, we did. That makes sense.
So the something you're referring to, is that represented in this plus log concentration of the conjugate over the acid?
I don't
Like conceptually speaking, because we calculated, maybe I'm getting things mixed up, but when we first did it and they were equal,
Uh-huh.
we got 4.7, yes?
Right. Mhm.
So is this an example where there wasn't a buffer, and now?
So it's still a buffer, but it's a buffer of different ratios. A buffer is as long as you got a mixture of these two. It's always a buffer.
So was it that this graph wasn't appropriate for the first problem that we made up, and that's the reason
Right.
why?
This one's actually got a little bit different, strong, because vinegar is more than 0.1 molar, so it's slightly different in terms of that. Okay. Now, so I've given y'all lots of buffer problems. Let me find you an FRQ that has to do with a buffer problem. Ooh, this is way too big. Hang on. It'll be easier for me to scroll if I do this. Actually, let's kind of go back and look at this one real quick. Below is the titration curve when 8ClO is titrated with sodium hydroxide. That's this titration graph. How do you know it's a weak acid? It's got a swoop, and we're starting up kind of high. Carefully draw a second curve that would result from the titration of 25 mils, same amount, of 0.2 molar, same strength, with 0.2 molar sodium hydroxide. If you use 8ClO4 instead of 8ClO, what would be different?
Well, now the conjugate base is worthless.
Yes. So what would be different about this graph if you started with a strong acid? Are we going to start at the same point?
Well, no, we'd be closer to 1 or 2 or 0. Somewhere.
So,
No swoop.
We'd start lower down, right? Because it's a strong acid, it's going to have a smaller pH. So we're going to start down lower.
No, mine would be straighter. It wouldn't have that like swoop.
It would be straighter, so no swoop. So would we reach the equivalence point still at 25 milliliters?
Yes, but you'd have a different equivalence.
Okay, why yes, though?
Because it's a stronger acid.
Well, but the equivalence point comes down to you got 0.2 molar sodium hydroxide, and you're still using 0.2 molar sodium hydroxide. It was 0.2 molar acid, it's still 0.2 molar acid. So the stoichiometry won't change. It should take just as many milliliters to get us to the equivalence point. So you're right. So we'd start down here with no swoop. When would we start to curve up?
About right
There.
Somewhere in here. And we would still end up here. Because at this point, y'all have to realize, this is the only thing that's in there at this point is strong base. We just keep adding sodium hydroxide until it just keeps, up and up and up. So, as long as you started down low, and as long as you kind of ended up the same place, you get the 2 points for the graph.
so how do we know that the HClO4 is stronger acid than HClO?
What are your strong acids? Hickel, Hibber, High,
We memorize them.
nitric, sulfuric, and perchloric.
Do the 3 oxygens, what are they?
I just know which ones are strong.
Morgan, memorize the strong ones, and if it's not one of those, it's weak.
Right.
Oh, okay,
Right.
okay.
Mm-hmm.
Okay.
Right? So, you had to do that. Now, here's a buffer question. Ooh, I should make that bigger, sorry. A student proposes making a buffer by combining sodium, and no one cares what the sodium is. It's just an ion that's a spectator. No one cares. Sodium perchlorate and perchloric acid. Explain why it's not a buffer. Now, sometimes they'll say, can it be a buffer? And you have to say yes or no. Right? They're giving you the claim. You may have to do claim evidence reasoning in like English class or something like that around here. They're giving you the claim. It's not a buffer. Tell me why. So if you may tell me
Perchloric acid is a strong acid, so its conjugate base is the ClO4 is worthless, and the Na doesn't affect it.
Okay. So it's a strong acid, and the conjugate is worthless. It doesn't do anything for pH. Okay?
And NaCl, no, never mind. See that fish is like-
Could you do it by definition? What is the definition of a buffer?
It has to be.
A weak acid and its conjugate.
Because neither one of those.
A buffer is a weak acid and its conjugate,
And that's a strong
and
acid.
HClO4 is a strong acid. So that can't be it.
And then NaCl4 is not the conjugate of.
Well, NaClO4 would be the conjugate because, here's why. The sodium perchlorate, you throw it into water, those ions separate in water, because that's what ionic things do. So it's a way of creating, you're throwing in, just like you can throw in acetate, sodium acetate. The business end of it is that perchlorate molecule. We don't care about the sodium. It's going to be a spectator floating around solution. Right?
It's likely you'll see a question like that, so I'm thinking if I'm a student right now, I would want to note that kind of a question with what he referred to as the definition of a buffer. And like put some asterisks by it so that I could look back at that before the test. Because that was probably 1 or 2 points right there.
Yeah, that particular one was 1.
Because like sitting here, you can have the feeling of understanding and then walk out the door and see this on the test, like, oh, I remember something about this, but then not be able to recall it.
So here's one from a couple of years ago. Just HF ionizes 13% of the time. Is that 100% of the time?
No.
If it's not 100% of the time, then it ain't strong. So HF is going to be weak. All right. 2 particulate representations are shown below. Which one is better at showing what happens in that acid and why? This triple thing right here is the hydronium ion, right? That's the hydrogen ion thing, the thing that water after it absorbs the hydrogen, right?
Figure 1.
Figure 1. And it tells you in the question, why is figure 1 better?
Because it's less disassociated.
It's less dissociated. According to this picture, how many of the HF molecules dissociate into ions? All of them. This would be a strong acid or it would be 100% ionization.
Figure 1, if you divide 7 by 8, you get about 13%.
Right? Use this to calculate the value of Ka. Well, let's just think about that for a minute, see if we can do it. What percent of it gets turned into ions?
13.
So if I told you the first initial quantity was 0.35, that's the molarity of it to begin with. What's 13% of 0.35?
0.05.
0.05? That's how much of it turns into ions. This value is also 0.05, because these are the 2 ions I made. So this is 0.05, this is 0.05, this is what you started with minus 0.05. So this is 0.05, this is 0.05, this is 0.35 minus 0.05. Plug and chug.
What do we start with?
It says the initial quantity was 0.35. I mean, I don't see the need to do that. My point being, at this point, can y'all push buttons on a calculator? And if you can't, I can't fix stupid, right? If you can't find the buttons on your calculators, I had a student one time who his 7 only worked about half the time, and I was like, maybe it's time for a new calculator. No, I can get it to work. All right, as long as you don't mind being wrong half the time, that's fine. He's like, no, it'll work. All right, as long as you don't.
Did he qualify?
All right. Here's one. We are mixing an acid with a base. Here's the titration curve. Determine the initial concentration of the HNO2. Determine the initial concentration of the HNO2. Well, this is a titration. Do y'all remember the titration calculation I taught you earlier? It was MA VA equals MB VB. Well, let's see if we can do that. All right, so what do we know? The molarity of the base is 0.1 molar. So the molarity of the base is 0.1. How much of the acid, how much of the solution did we start with?
100 milliliters.
100 milliliters.
So,
So the volume of the acid is 100 milliliters. You don't have to change it to liters unless you're real excited. As long as they're both milliliters, it works fine. So VA is 100 milliliters. MB is 0.1 molar. So the question is, how do we find the volume of the base? How do we know how much base we had to add to titrate this thing?
You were going to
Where it's right.
According to the graph, how much base did we have to add to get this thing to be titrated?
20 milliliters.
We look for the equivalence point. How many milliliters did it take to get to the equivalence point? 20 milliliters. So the math is MA times 100 milliliters is equal to 0.1, the molarity of the base, times 20 milliliters. You may get an answer.
0.02.
So 5 times weaker. Is that right? 0.02? All right. So that's what y'all got, 0.02. Estimate the value of pKa for this acid. Nope, don't need to find Ka.
It's equal to the pH at the half equivalence point. So
Find the half equivalence point. Gosh, you're getting sharp. Find the half equivalence point. I'm teaching you not everything about buffers. We're teaching y'all not to answer questions on the AP exam, right? So the best gauge of that is give you AP questions, right? So, what's the half equivalence point?
10.
10. And what's the pH at the half equivalence point?
3.3, 3.4,
Yeah.
between 3 and 3.5.
Okay, you can't say, you're gonna need a number, so let's decide on a number we can all live with.
3.4.
Okay, 3.4. During the titration, after a volume of 15 milliliters is added, which species, the acid or the conjugate, is present at a higher concentration in the solution? After 15 milliliters has been added, which species is more present? The HNO2, the acid, or the NO2, the conjugate base? So that would be over here. There's more of the conjugate base. We've used up more than half the acid. So more than half the acid is turned into conjugate base.
So if more of the acid, or more,
Go ahead.
if more of the, hold on, that didn't make sense after it was going to come out. Never mind.
Okay. Well, if you think of it again, bring it up.
So this is one that you would not be able to tell that it was a weak acid just from looking at the graph. You have to know. That
The swoop is there, but it's ever so slight because this is HNO2 is a stronger of the weak acids. The weaker the acid, the more present the swoop, and I won't get into why, but
I remember what I was gonna say.
Yes.
If there's more base there, why is the pH still in like the acidic realm?
because remember the acidity or the pH is a measure of, or is a result of mixing together the acid. There's still some acid present.
Mm-hmm.
It's just not as plentiful as that conjugate base is. And the conjugate base, we're not saying this conjugate base and this acid are equal strength,
Okay.
right? So, like, how many of you would it take to overpower some very, very strong person? Well, maybe more of, but, you know, we're just talking about pure numbers. We're not talking about, the acid in this case is much stronger than the conjugate base is. I mean, it still does something, we just don't know how much, right?
Thank you.
So, after 15 mils, we get that. Now, according to that, the thing we're missing is a couple A, B, C, D parts. How many points do you think that is worth on an FRQ? How many points do you think E subpart I is?
1.
I got one. Anybody else?
Like 0.5.
This is a 10-point question, so we're missing A through D, but
one.
one? Okay. How about the estimate the value?
One.
Probably one. I usually get somebody to be like, half. Not how the AP exam works. You know, point two. And how many points do you think for that last part?
2.
Two.
Okay, so let's look at the rubric. So you get 1 point for the calculation to say 0.02. MAVA, MBVB, point. Estimate value pKa, about 3.4. How do you get that wrong? 4.7, 2.3. Now, before I came, if I asked you to estimate the pKa, what would you have made up?
Probably, I don't know. I was gonna say something. It looks like pH.
Right.
I,
Do y'all remember kinetics? And there was 0th order, 1st order, 2nd order? Remember back in the day? So I had one time a bunch of graphs, it was Robin too, a bunch of graphs and it said, what order is this? And they said, well, I put this graph first, and then I put this graph, and then finally I put this graph. That's the order that I would go in. And I was like, Lord. So it's like not even close. All right. 1 point is earned for the correct choice and justification. It's past a half equivalence point. There's more conjugate base. 3 points. On this question in 2018, when they gave it on the national exam, the average was 4.2. You think you could have picked up one more point somewhere in A through D? Hopefully.
Wait, what are you saying?
On the 10-point question, the average is
But which
4.2.
okay, but do we know where those points came from, or just
Well, right now I'm just showing you 3 of the 10 points possible. If you can get these 3 points, because I don't think any of this particular one was crazy hard. You know, look at a graph, figure it out.
Yeah.
Could you have picked up 1 or 2 more points on other parts of the question? Probably so. What's the average score on an AP exam? 3. What's a passing score? 3. What's your goal to do better than average on every single FRQ? Your goal is to get every point. But we know that's highly unlikely because there's usually 1 or 2 people per year out of about 85,000 that get every single point on every single question. So it'd be great if that was you. It's never going to be me because I choke under pressure. So, all right, let me see if I can find another one that has pictures. All right, can y'all tell me the equivalence point of the milliliters?
13, 14.
13, 14, good. And what's the pH at the equivalence point?
9.
9. When the pH is above 7 at the equivalence point, what does that tell you about what's being titrated?
A weak acid.
It's a weak acid. What's your other clue that it's a weak acid?
The sugar.
Swoop. Okay. Write a net ionic. I assume in 4 y'all did net ionics. You can go back to calculate the molar concentration of the NaOH. So you'd have to know the molarity of the acid, the volume of the acid, and the volume of the base. It's still MAVEA equals MBVB. This one asks you for the molarity of the base. Explain how the student can estimate the value of Ka by using the titration curve. It's a weak acid titration curve. Where can you know the pKa? Half equivalence point. What is the pH at the half equivalence point?
4.8.
Like 4.9.
4.8, 4.9. If that's the pKa, how can y'all find the Ka?
You do 10 to the negative.
Right, you do the opposite of the log step. So instead of taking negative log of it, you go 10 to the negative Ka value. Did the question say find it, calculate it?
No, it just says how.
Explain how. Half equivalence point, the pKa is equal to pH. Take 10 to the negative pKa value. That's how you can find it. How to make a solution. Trying to find one in particular that's okay. All right. Student is asked to make a buffer with the pH of 3.4. What's the pKa of said acid? 3.4. When the pH is equal to the pKa, what does that tell you? Half equivalence point. That's always the answer. That in Coulomb's law. Always the answer. Explain why the addition of 0.1 molar NaOH to the weak acid can result in the formation of a buffer. Well, we already said that. When you titrate a weak acid, what does that turn into?
Conjugate base that does it.
Conjugate base that does it. I mean, it creates a mixture of the weak acid and its conjugate, which is the definition of a buffer. Determine the volume in milliliters of 0.1 molar. The student should add to 100 mils of 0.1 molar HNO2 to make a buffer solution with a pH of 3.4. So if you've got 100 mils of it, and they're the same strength, it's 0.1 and 0.1. How much base would you have to use to get to the equivalence point? If you had 100 mils of the acid, how many mils of the base would it take to get to the equivalence point where everything's all titrated, everything's done? 100 milliliters. So how much would it take to get to the half equivalence point?
50.
50 milliliters.
And that's what 3.4 is?
At 50 milliliters, you've reached that magical half equivalence point where the acid and the conjugate base are in equal concentration, and we know at that point the pH is equal to pKa. It told us up above that the pKa of the acid was 3.4.
Okay.
All right.